The recording, start the show. So thanks for coming back. I appreciate it. I've got example 2 here to show us, and I've been fixing the typos and things that I found from yesterday's example. I've already found a couple today looking back through this, so I will update the handouts and all the materials with the fixed typos after the end of the session. That was one of the best pieces of advice I ever had as a student. It's like, no, when you find typos in your teaching material, you fix them immediately, because otherwise they'll still be there 2 years from now when you come back to teach the class again. So there was a typo this year that someone found that had been there for at least 10 years, and no one had caught it. I was really impressed. It was like, wow, that made it through a whole lot of quality checks. But you never see them until you're presenting. That's the rule. That's how it works. So this example is the second example. It is based off of my master's thesis, which again was never published for the purpose that it was conducted. It was subsequently published as an example in a tutorial on how to fit mixed effects models for experimental designs. So this one is a little more complicated than the last one, but it's the same premise. We still have the idea of subjects and items as crossed random factors. So in this example, what we have, let me see, get past the table of contents here to my paragraph. So this is the same data set that was used in chapter 12 of my book, which I had sent you all last week. The outcome is response time, but these response times are really long because it takes a long time to find the change between two images that are presented in a flickering paradigm. So we log transformed it to give residuals to reel those in to make the level 1 normality assumption a little more plausible. So these are older adults and younger adults are the subjects that we have here. The younger adults are your typical introductory to psychology pool where they have to do research participation in exchange for course credit. The older adults theoretically are healthy community dwelling older adults. In practice, who they tend to be are retired faculty and their spouses. So the younger group is you're laughing, I'm not kidding. Like we had a database of people like emeritus faculty and we'd call them up. Hey, do you want to come, press a button as fast as you can 100 times? And they're like, sure, where do I sign up? But no, this isn't that kind of attention task. This is a visual search task. So I showed you an example of it last time, but just briefly, there's a real world image, like taken from the front seat of a car with a camera, and it's presented for 280 milliseconds, I think, followed by a blank screen for 80 milliseconds, repeat, and then there's a new version of the picture where one thing is different, presented for 280 milliseconds, then 80. So it looks like it's a picture that's just blinking at you, and the blinking helps disrupt whatever normal orienting processes would be happening to help you find the change. So in this case, it's a very slow serial looking through the picture to find the change kind of task. And there are some inaccurate responses in this example, but they're not because they got it wrong. In most cases, it's because they did not find the change before, I think it was 45 seconds was the maximum that was allowed. So definitely not missing completely at random. They would be more likely to miss the changes that are more difficult to detect. So we do not have complete data in this case. So in addition to subject age as the primary variable that we'll be interested in modeling as a predictor, we also have 2 ways in which the items, which are these natural scenes, differed from each other in terms of the characteristics of the change that was made to the scenes. One of them is how relevant the scene's change would be to a driving experience. So for example, if I showed a sign that said there's a stop sign versus not a stop sign, or a signal light versus not a signal light, that would be really important to pay attention to. If I messed with some trees off to the side of the road and now there's 3 trees and now there's only 1 tree, you probably wouldn't be paying attention to that. So the theory would be that things that you should be paying attention to will be detected more quickly. The other is salience, and in this one, it's just literally like how obvious the change is from a visual perspective, how much of the screen did it take up and that kind of thing. In this study, both of those characteristics were rated by other subjects, and so on a scale of 0 to 5, they rated the relevance to driving and the salience, and we took the mean ratings out of those and used those as the item predictors. So in contrast to the previous example 1, where we had this neat 2x2 design in terms of kinds of items, we don't have that here. We're treating salience and relevance as continuously varying item predictors instead. For age, we're going to do something a little bit different, and I will show you the coding for that when we get to that point. So, all right. Any questions so far on the story? Okay. Then loading packages. Matrix and Elmer threw me off yesterday when I was loading this onto a different computer, so I had to redo that. We're using the same stuff as yesterday. We're going to be using the Elmer function from LME4 and Elmer test to get additional pieces using residual maximum likelihood and Satterthwaite degrees of freedom. I did think of one more reason, by the way. Someone asked me this question yesterday about whether I prefer NLME versus LME4. In my experience, NLME has a more difficult time rendering correct Satterthwaite degrees of freedom in different kinds of models. I have been unsuccessful to get that to work, and it throws error messages, whereas the same exact model runs just fine with Satterthwaite degrees of freedom under Elmer, so that would be another reason to prefer it. In this case, we're not going to do anything fancy with the R matrix in terms of heterogeneity of variance. I tried and failed, as I have a note about that, so we're going to stay in Elmer for this one. So importing Excel data, in this case, the Excel data file that I'm using called example2 has two different sheets in it. One of it is the data, and the other is going to be a data set of fake people that we'll use for plotting purposes down the road. So I'm importing the one called data in this case. Log transforming response time, again, to help with residual normality as an assumption. And then for age, I am building what I would like to call either a piecewise slope or a semi-continuous way of specifying this as a predictor. So within the younger adults, there's very little variability in age. Most kids are between 18 and 21. Within the older adults, they varied from, I think, 63 up to 87. So there's not just older, right? There's a lot of variability in that. And what has been done in the cognitive aging literature that I was familiar with is they would artificially group older adults into young old, which is anything up to 75, and old, which is past 75. Well, I don't like that approach either, because there's nothing magical about 75 as a dividing line. So we do really have distinct groups when it comes to younger versus older, because there's no one in the entire midlife point of their life, but we don't really have groups when it comes to older. So what I'm going to do is create one variable that keeps track of how many years past age 65 they are if they're in the older group. And I picked 65 because that's sort of like a conventional, in the United States at least, retirement age. That's when you're eligible for benefits that go with that and that kind of thing. So it's just a convenient reference point. So I have one predictor that keeps track of whether they're in the younger group or the older group. So that's a dummy code called older. And then I have a new one that I'm building here, which is years 65, which is age minus 65 if they're in the older group. So the idea then is that we have one slope that gets us from the younger group to the older group, and then a second slope that steps in and distinguishes continuously varying age within the older group. So you can think of that as a piecewise slope or a spline model. Semi-continuous is another word that I've used for that. So does that make sense in terms of that coding scheme? Okay. Another way you can refer to it is as a nested effect of age, because the differences as a function of how exactly old you are only happening within the older group. So that slope is somewhat nested in that older cohort. Relevance and salience, because they were on a scale of 0 to 5, I centered them near the middle, 3. That's just a convenient choice. And anytime that you're centering at constants like this is only to provide meaningful interpretation of your fixed intercept as well as a random intercept in the event that any of these become random slopes, which they will be in this example. So there's no wrong constant to pick per se, it's just a matter of convenience and what your parameters actually mean with respect to your fixed effects. Also selecting some complete cases with respect to all of the variables that are going to be modeled. That allows me to use the AVE function down here to average over subjects and items to get some descriptive info. Okay, so in terms of the variables that we're modeling, log RT ranges from a minimum of 0.1 to 4 in a log scale. I don't really have any sense of what that translates to into actual seconds, but that's okay. The mean is 1.61, so we'll see that reappear. Relevance then ranges from 0 to 5. Salience, of course, and then age ranges from 18 to 86. So that's the one we're doing with the piecewise model. So first thing I did then is compute subject mean response times and the number of trials or item responses that each subject had. In looking at that, we see a considerable range in the average time that it took to complete this task for a given subject. So some subjects are faster than others. And in terms of the number of trials or items that each person contributed, it ranges from 43 to 51. So 51 is the most. Some people have 43. Instead, those would be the people who are less able because they would have missed those response times because they never found the change to the picture. So the ones that are least relevant and least salient would likely be the ones that are the most likely to be missing. Doing the same thing for items in terms of getting their descriptive information, we see again a large range in mean RT, as well as differences in the number of subjects that we have item responses for. So up to 153 at the most, and then some items only have 143 subjects responding. Again, those would be the most difficult ones. Okay, so ready for variance decomposition? Or variance partitioning? My husband doesn't like it when I say variance decomposition because it sounds like a dead body decomposing. Like decomposing is never a happy word, right? It's always referring to something falling apart. So partitioning is a more neutral, slightly happier word. But the idea is we're trying to figure out how much variance we have of each kind that will logically build or guide our model building, because you have to have variability in order to be able to predict it with additional information about the person, about the item, or both. So I am stepping ahead in terms of empty model land to just empty model 3. The reason that I can do that in this context is because the RENOVA function will fit the alternative models without each variance component, so I don't have to do that manually in this case in order to get a log likelihood by which to compare their fit. So we're starting with a model that has 3 piles of variance, keeping the same notation as yesterday. So the first subscript T keeps track of which trial we're on. That's the unique combination of subject and item response. Then I keeps track of which item it is, so which scene they're responding to in terms of detecting the change, and then S is for which subject it is. So this is one thing, by the way, that my students sometimes get confused, and in my own notation, like if I look back at older stuff I've done, I screw it up sometimes. Note that there is a little s here because this is a specific U value for subject S. So like that is one number that each person would have that runs through all of their predicted outcomes. Likewise, this is a little I here because that is for this particular item. This U would be one number, and E would be one number as well for that trial, for that item, for that subject. Then when we get to the variance components, the way that I notate things is that I like to say what it is the variance of as part of the symbol so that I don't have to memorize that. So tau squared is a universal level 2 variance notator, so to speak, but I have UOO with a capital S here to try to indicate that it's not a variance for one subject, it's the variance across subjects. So if you picture like little s as an index for which subject and then big S for all of them. Likewise, I'm using capital I for the variance across all the items. So this variable, this random intercept right here for items is distributed this way. This variable is distributed that way, and this is that way. So 3 different sources of variability. In terms of what could be coming next time, what I had sort of tentatively planned, is how these same models would look in terms of binary outcomes. So if you're familiar with logistic regression or item response theory models, those kinds of models, in those models, we would not actually have an estimated residual variance. Because when you have a logistic function, it's fixed to a value. Pi squared over 3 is the variance of the logistic distribution. If you have probit, it's fixed to 1. So the fact that we're using a normal conditional distribution is why we have a separate level 1 residual variance in this case. In those same models, though, we would still have separately estimated variances at level 2. So even if level 1 has a fixed variance that's tied to its mean, level 2 can still have estimated variances. So just foreshadowing that coming up later. So to fit the model then, we've got log RT has a fixed intercept, a random intercept variance is how I would refer to the parameter for across subjects and across items. And the numbers are much smaller today because this is the log of response time in seconds, but we can still get a sense as to relatively how much each source is by staring at these things. So level 1 residual, that's the 0.39, that's the variability across the e's. The 0.16 there, that's the variability across the items in their mean responses. So 0.126 then, conceptually, is all the reasons why some items are responded to faster than others. For subjects then, 0.18 is all the reasons why some subjects are faster than others in giving their responses to these items. And one thing that I found was interesting is I literally borrowed the same code as I did for example 1, pasted it in here, in which I wrote subjects first and items second. In example 1, it put items first and subjects second, and in this example, it put subjects and then items. It must be tied to which column is first in the data set. That's my theory. But the arbitrariness of this I wanted to point out, because when I first started building, saving objects and trying to compute things manually, I wasn't getting the right answers. And I figured it out that because it switched the order, I had to switch which rows things referred to in my code from yesterday. So when you're saving results out to do things, it's good to print them just to verify like which row is which, because it isn't necessarily the order in which you wrote it or the order in which you'd expect it based on similar code and similar data. So fun things. I like to call such things job security, because if they made it easy to do this stuff, then everyone could do it, and then we wouldn't be employed. And so this is me keeping my job by learning all the tricks and tweaks of various software packages. 1.63 is the fixed intercept, so that's very close to the original mean, but it's not going to be exact. So I would interpret this number right here as the mean of the subject means and the mean of the item means. So it's a weighted mean with respect to both dimensions. So that's our naive jumping off point for what we would expect log response time to be for any item for any subject. Intra-class correlations then, so we can turn these numbers into proportions to get a sense as to relatively how much is due to each source. For this, I'm still using the ICC function from the performance package, but I'm adding an extra command here. So by group then gives separate ICCs for each dimension. If I left that off, it would give me one that adds the both together. And that one does not have, I think, as useful of an interpretation. That would be the expected correlation of trials from the same subject and item, but in this case there's only one, so that doesn't make a whole lot of sense. So instead what I did is ask for separate values. So subject intercept variance, then I would compute the ICC for that using the subject variance as the numerator, the total variance across the three as denominator, and that's where that number came from. Same thing with the item one. So relatively more variance across subjects, but we do still have item variance, which means both of these random dimensions can potentially be explained by predictors. And then here is what I was referring to before, printing varchor to make sure I have the order of the rows right. So subjects were first in this data set, which means that when I go down here to try to save each variance component, I need to make sure that I'm pointing it to the right row. So row 1 and then column 4. And Anna has a question. Go for it. Anna, excuse me. Got to get my right accent going today. Go for it.
Don't worry. Can you quickly repeat? So the ICC for subjects means the variance. I'm always thinking in the between person and within person variance, and I've struggled a bit to apply it to this example. So there was what was it? 25% is in the different scores is due to differences between people, and then the other one is it means 80% of the variance is due to differences between items, or
yes. So 26% is subject random intercept, which is subject mean differences. So that would be the between part that you're used to, but I'm using words that are more specific because there's going to be more than one kind of between variance. There's intercept variance and there's slope variance. So at this stage, we're at intercept variance, and in the absence of any random slopes, it's mean differences across subjects. That's what that means. So in English, some people are faster at this than others, and that's 26% of my story. Likewise, some items are easier to find the changes in than others. And the differences between items in their mean response times is another 18% of the story. And then whatever's left, can't do the math in my head, but I knew I would need to. 56% is, that's a technical term. You got to do the gesture with it. The people on YouTube are missing out. That just means it's something about the trial and the interaction of the subject and the item at that moment. So we can't separate out what is subject by item reliable variance from what is just fluctuating trial within item within subject variance, because we only have one exemplar of both. So yesterday someone had an example where there were 4 trials of each kind. In that case, you could separate out what is subject by item interaction variance from what is trial specific residual variance, but not if you only have one. So then let me ask some questions. What kind of information do you think is capable of explaining this 26% of the variability in RT due to subjects? What kind of predictors?
Some kind of person predictors, like their age maybe or whatever.
Yep, that's what I got here. Yep. So between person mean differences can be explained by between person variables, things that are constant to the person, because this is a constant summary of their performance. Likewise, what kind of characteristics do you think can explain the 18% due to item mean differences? Charlotta, go for it.
Yeah, the relevance and salience or other item level predictors.
Ding, ding, ding. Relevance and salience or any item level predictors. And then what kind of things would be able to explain the remaining 56%? Any guesses? It's the T for trial. Go for it, Sabrina.
Nothing that we have here because we don't know what variance source it is attributed to. But if we had other factors that we could take into account, maybe we could explain it.
I will say that is theoretically correct, but in the way that the models are going to work out, we can't explain it. Stay tuned. Dun, dun, dun. It would have to be trial-specific information. So, for instance, if you randomly assign the order of these trials, which they were, maybe you're slower to do the task at first, and then you get better as you get more practice. That could be a trial level 1 predictor. That would explain the remaining 56% of the variance. Alternatively, you could be keeping going and going and going and get really tired of it and get slow and more error prone, like that. Opposite way of having a trial order potentially mattered. There's different mechanisms for that, but it'd have to be something that's either trial specific or combination of subject and item specific. And it's the latter that's going to turn the story a little bit more interesting. So stay tuned. Dun, dun, dun. All right, so we get the numbers. I wanted to show you how to get the ICCs directly, but I also had an ulterior motive. So at this step right here, what I'm doing is saving each of those 3 variances to use as a baseline and computing a pseudo R-square. So this is going to be a baseline against which to judge how useful my subject predictors are, how useful my item predictors are against this as all the reasons why subjects differ in their means, all the reasons why items differ in their means, and then the remaining 56% for the residual. In terms of significance tests, I mentioned this earlier, but I'll just make the point. Is there anything in this output right here that tells me if I actually need these 2 random intercept variances? Is there anything that you see directly that would be like a p-value right in front of us? Nope. What do we need to do instead? Starts with an L.
The likelihood ratio test.
Yes, which is actually not a ratio, it's a subtraction. Or a minusing, as my son would say. We do plussing, minusing, timesing, and then dividing. So what Renova is going to do for you, if you're not feeling Renova by it, I should say, or Renova by a tornado, in my case, see, we call that a callback, it is going to fit the alternative model without each of the random intercept variances for us, tell us what the log likelihood would be, and then do a significance test on that. So in this case, if we removed the subject random intercept variance, our model log likelihood would get shorter by 2,360. So that is going to be p to many, many decimal places. Likewise, if we remove the item random intercept variance, our log likelihood would get shorter by about 1,900. So definitely need those things, and I would report that test like this. So -2 times the difference in log likelihood with 1 degree of freedom. So in this case, I could do the mixture chi-square thing, but it really doesn't matter. If the test is significant with the straight degrees of freedom, then it will be significant with the mixture. This is just a little bit more conservative. In terms of descriptive, I think it's helpful to compute confidence intervals, but these are not confidence intervals around the fixed estimate, not describing the precision of the estimate across samples. It's describing the range of the intercepts across subjects and items. So the fixed intercept would be the center point, which is 1.622 in this model, plus about 2 standard deviations. So the first one is for subjects, so we put the subject random variance in there. The second one is for items, so we put the item random variance in there, and then we get these ranges. So then the expected intercept in log RT for 95% of my subjects should be somewhere around 0.8 up to 2.5, and then for my items would be between 0.9 to 2.3. So that gives you a sense in the metric of the outcome how that variability translates into differences between subjects and differences between items. And then I made those in R the long way as well. So saving things and then doing the manual computations of that. Is this kind of thing something that you know how to do already, or do I need to talk more about that? Like saving stuff out of the output and making it to do math and stuff like that. So we're shaking your head, meaning I don't need to talk about it, or you don't know how to do it. The second one, you don't know how to do it. I didn't either. That's why I make a point about this. So when I build my teaching materials, I usually teach in more than one package. So historically, for these types of models, I had been teaching in SAS and Stata and R. And because of that, I end up building an Excel sheet where I do all the computations, so I just have to do them once. But in practice, nobody wants to hand enter a bunch of numbers. It's error prone, you would have rounding error, and so forth. So I think it is good to figure out how to access the saved output. And I am very, very bad at figuring that out, to be honest. And I usually end up asking my husband for help, who's much better at it, or finding other people's examples. But the trick is inside R, when you save the results of a model, you have to go in and navigate down through all the pieces that are saved and try to figure out where stuff is. So in these models, the two things that you need basically just to learn, I think is fixf is where the fixed effects are stored. You'll see more tables that are printed with that. And then we have, where is it? I already did the variance components up here. Varcore is the function that returns the model variance components. And so I set it up so that I could access it as a data frame rather than a table. So this then is what the code below is operating on. So this is saying I would like to compute a total of the 3 numbers that are in this column right here. So I am referring to it as a data frame, which means I refer to as rows and columns. So 1, 4 is row 1, column 4, which is that number right there. Likewise, row 2, column 4 is the one below it, and then 3 is that. So then what's happening is the number that is the result of adding these 3 together is now saved as a new object in R. Some people call these objects, some people call these variables. I don't want to use the word variable because it makes it seem like it should be in a data set somewhere, but it's not. It's just like floating in the program. It's like a program variable. I think of it as a placeholder. So it's like when R comes and sees this, it's going to insert whatever number is attached to it as almost like a find and replace that happens dynamically. So this type of code is very useful to generate at least once, then you can reuse it and probably build functions to do things a little more efficiently. I'm not at that stage yet. I'm still working on that. But this is saving the total variance so that I can then compute intra-class correlations. This is saving each one of them as a separate programming object so that I can use it to compute pseudo R-squares down the road against this model when I start adding stuff. I didn't need to save anything for Renova, just print it. And then I tend to print labels with things so that even if the program itself doesn't give good documentation, at least I know what my purpose was in estimating it. Okay, I'll show you some more of the programming stuff here. So then the confidence intervals, I had to go into fix F, and there's only one fixed effect, so there's only one number it could be. So I saved the fixed intercept as this thing right here, another programming object, and then computed the confidence interval as plus or minus 1.96 times the standard deviation that's implied. And let's see, this one, yep, this is the minus and that's the plus, so these are the subject ones. And then down here, I replaced it with the item variance object, instead of the subject one, and there's the plus and the minus. Okay, any questions on that so far? Nope, cool. All right, moving on. So next stop, conditional model 1, I'm going to add in my item predictors. And because the point of this was we were expecting an interaction, I went ahead and added that first. So I have log response time, TIS, and why, somebody tell me why is my subscript for this item predictor 010? What's the logic behind that? And I'll have some more coffee while you think. Charlotta, go for it.
Yeah, I think because it's item level and then it kind of counts upwards. So first predictor at the item level.
Exactly. So relevance is the first predictor of an item at the item level. Salience is the second predictor, and then the interaction term is the third. So which order you put these in is up to you. And honestly, across my materials, sometimes it's like TSI and sometimes it's TIS because they're both level 2. So they're pretty much interchangeable. But if you're going to use the subscripts, then I would go to the trouble to put the zeros in the right places, because then this tells me, based on the notation, pretty clearly that this is an item characteristic, this item subscript, and the fact that it has a number in the places where the items are. So in this notation scheme, main effects will have a number in only one spot, whereas interaction terms will have a number in 2 different places. So we'll see that as we build the model. So this has all 3 piles of variance. We have our new item predictors. So we're going to throw those in right here, writing it out again the long way to emphasize that we need both main effects and the interaction in order for the interaction to be interpreted correctly, same as in any linear model. We go down here and let's try the results. So to remind you, relevance and salience are item characteristics. They both range from 0 to 5, and they're both centered at 3, which would be so a medium level on both dimensions. So let's go through this. Who's feeling brave? What does my intercept represent in this model? And if you don't want to talk, you can type too. Up to you. What does my fixed intercept of 1.61 represent? Go for it.
It's the expected log reaction time if both predictors are 0, and because they are centered, it's the mean. So it would be expected log reaction time for medium salience and medium, what was the other?
Relevance, yes.
Predictor?
Yes, relevance and
Relevance, yeah.
salience. Rel and sal to be. I like to name my variables so that they're all the same length so that things stay nice and orderly in the code, but that's just my own, twist. Exactly right. So these, I wouldn't say they're mean because that's not the exact mean of these 2 predictors, but medium is good enough, like mid-level, I would say, in terms of the rating scale. And then what happens if a change has higher relevance? What happens to your predicted response time? This will be a finger question. Does it go up or does it go down? Down, yeah. So changes that are more relevant to driving are detected more quickly, so lower response times. And for every unit more relevance on this 0 to 5 scale, the log response time is expected to go down by 0.05. Now, is that the end of my sentence, or do I need to keep talking to make it correct? What do we think? With everything else remaining equal, I will say that is correct, but do I need to keep talking still? Is there more to it? For every additional unit of relevance on the rating scale from 1 to 5, log response time on average goes down by 0.05, with all else remaining equal. At medium, yes. So this is not the relevance slope per se. This is the relevance slope specifically when the interaction term drops out, which happens when the interacting variable goes to 0. So this is the effect of relevance for items that have medium salience changes when salience is at 3. Likewise, this one is the effect of salience. So the more salient the item changes, the faster it is detected, all things being equal, and then conditional on relevance being 0 as well. So this is the effect of salience in medium relevance changes. And the interaction term at this point is not significant, but we're going to interpret it anyway, because that's not going to be the end of the story. Is it making these two main effects stronger or weaker? What do we think? I got 3 minus signs. That's your clue. Is the interaction term making the main effects stronger or weaker as the other variable increases? Not sure. Should we talk about it? Yeah, let's talk about it. And by let's, you mean me? I figured, but we'll use the royal we, as they say. We will talk about it. So remember, there's 4 kinds of interaction patterns, right? An interaction takes its main effect slope and makes it more positive, less positive, more negative, or less negative. If it's either more positive or more negative, then it's strengthening the slope. It's moving it further away from 0. If it's less positive or less negative, then it's weakening the slope and moving it towards 0. So in this case, what would happen is each of these main effects is negative, so the story is the same, but we can do this one to start with. So this is the relevant slope specifically when salience is 3. For every unit additional salience, the relevance slope becomes more negative by 0.01. So it would be 0.05 to 0.06 to 0.07, so it's strengthening the effect. Relevance has a stronger effect on response time in changes that have higher salience levels. Non-significantly, but that's the pattern. If we go the other way, then I would talk about what happens to the salient slope as the unit of analysis, and I would say that salient slope is specifically for relevance of 3. It also becomes more negative by 0.01 for every additional unit of relevance. So the salient slope also becomes stronger in changes that are more relevant to driving. So the term that people would use to describe this pattern is over additive, like there's an extra something that happens with the two, as opposed to a less positive or a less negative weakening the slope would be under additive, like it doesn't have as much of as a boost as you would expect from the two. So if you were going to put more, I would say GRE words on this as opposed to more positive, less positive, etc., I could say something like the effect of relevance is enhanced in high salience items, or the effect of salience is enhanced. The effect of relevance is magnified, is strengthened, like pick your favorite word for what more negative would be. But in this case, a negative slope is a good thing because it means you're making the response time faster, lower, however you want to say it. Yeah, so this one is, these are both more negative in terms of the patterns. Okay, does that help a little bit? Maybe? Okay, we got more interactions coming, don't worry. They're one of my favorite things to do. I know that sounds weird, but how many of you teach on a regular basis as part of your appointments? Most of you? Some of you? Yes. Do you have some things that you like teaching better than others in content? Like some days you're like, oh, I get to talk about this today. Yay! Because I do. There's some things I like talking about better than others. I like talking about interaction terms quite a bit. I like talking about piles of variance quite a bit. I hate talking about estimation and likelihoods and stuff like that. But interaction terms are my jam. They're going to be your jam too. So I'm not asking for any simple slopes in this example because there's no obvious point at which you would want to know. Like, what is the effective relevance at 4, at 5? Like, these are sort of arbitrary numbers, although I could do that if you wanted to. But we're going to keep adding to the model because the story is not over with. So in terms of the role of these predictors, let me get all the variance components on the screen. Which of my 3 piles? Oh, got a question first. Go for it, Anna.
I'm so sorry.
Oh,
I
don't be
still don't
sorry.
understand. Why is a negative estimate in this interaction meaning that my slope becomes more negative?
Let me, do I have, let me see what I did. I don't have it in here. Let me start typing. See, this is why I have a Word document. I can explain this. So if I wanted, so Alt equal in Word and in PowerPoint is how you can make an equation. Do you all know how to do this, by the way? Is this another thing I can teach you? You don't know how to do it? How to make pretty equations? It's very cool. Trust me, it's a lot easier than doing it with the Hunt and Peck method with the special symbols. Okay, so I'm going to go up here to grab this equation to save a little bit of typing. Nope, too much. Lo siento, I'm getting trigger happy. Just that piece. There we go. Okay, we're going to come down here. Type equation here. Don't mind if I do. Maybe. It's like, no, I mind. You can't. No? All right, fine. So if I have log RT TIS, okay. Let me move this to the middle so we can see it a little bit better. So do you see what I'm typing inside the equation editor? And I have an underscore TIS. If I hit the space key right now, it renders as a subscript. Equals, now I need to go find my Greek letters. Well, you can go up to the equation menu and scroll through all the different letters and things that they have, right? So there's all these choices, which takes forever. Or you can just type what they're called. So if you hit a slash above the enter key, like that, and then gamma is the symbol that I'm using for fixed effects, again, hit the magical space, and it renders. So this is LaTeX, I believe, as the underlying technology here. I need 000 for my fixed effect, plus we're going to need another gamma for the first item predictor, nope, times rel sub I minus 3. So by the way, this idea, I'm showing the reader the centering point so that they know what 0 means explicitly. I find that to be helpful when I'm showing things here. Do this, gamma 020, sal with an underscore I minus 3. One more, almost done. Gamma 030 for the third thing, rel underscore I minus 3, and then sal underscore I minus 3. Okay, that's my ingredients for this model. So what do I need to do if I want to figure out what the relevance slope would be for any level of salience? What do I do first? Well, if I would need to know the slope of relevance, if that's what I need to go find all the terms that have relevance in here, and only those. So that means I need that one to start with. Come on. My keyboard does not want to hit paste today for some reason. Please? It's like, no, I'll render your equations, but you're not allowed to paste. You get to write it out by hand. Okay, fine. Rel slope equals gamma 010. So I need that at a minimum. Do I need gamma 020 to figure out what the relevance slope is? Nope, because that doesn't have anything to do with relevance. Now, do I need the interaction term to figure out what the relevance slope is? Yes, I do. Okay, so I need gamma 030. Now, I want the relevance slope, which means the interaction term would be activated through the moderator, which is the other variable, salient slope. So then it would be like that, -3. So those are my ingredients. So then if I put some numbers in here, let's say this one is -0.05 plus -0.01, like that. So let's say that I want salience of 4. What number do I put in here in the bracket? If I want the relevant slope, I need a 1, right? So if I do the math then, the result is a slope of -0.06 within my adding capabilities, right? What if I want the salience slope for 5 at the top of the scale? What do I put here? If I want the relevant slope for salience of 5, then I put a 2. So then now my slope is even more negative. It's 0.05 plus 0.01 times 2. Okay, I'm seeing your face. You're like, oh, that's what it is? Yep. Now, what if I wanted to plot it for a salience level of 1? Could I do that? Sure, I could. If I wanted a salience level of 1, what goes in this parenthesis? -2. Now, the slope would be getting less negative as salience goes down. It would be getting more negative as salience goes up. What's this? Does that mean good? Okay, I only speak thumbs. I don't have actual sign languages as part of my vocabulary, unfortunately. Although I do know a few things from having a toddler. All done. Please. This is his version of it. And thank you. Got those 3. If I wanted to do the salient slope, what would I need to change?
Changing it to gamma 020, and then for the interaction term putting rel instead of cell.
Exactly. So then this number would change to about 1,4, and the interaction term would stay the same. But now what we plug in here is the value of relevance that we want the salient slope for. So it's always the other one, the moderator. Okay, so relevance and salience help each other, essentially. There is a larger there's a larger decrease in response time when both of these are high than you would expect from just each of them being high additively. It's an over additive interaction term. Okay, cool. This table, by the way, I never ever need. I don't know why it prints it, so we'll just skip over that. Okay, now I know where I was going when, let me put this back to left aligned. So it looks, there we go, that looks better. So I added 2 predictors and their interaction, right? We agreed on that? That's what just happened? Cool. Which of my 3 piles of variance should those 3 fixed slopes have explained? Subject variance, item variance, or residual? Item variance, 1 vote. Anyone else want to vote? No one's voting. Well, they're item predictors. It's going to be item variance. Yep. It really is that straightforward. For main effects, mind you. Main effects only. So come down here. I have the item variance from the previous empty model, that number, minus what it is now after adding in the predictors, divided by what it was before. And so I have officially explained 26% of all the reasons why some items are responded to faster than others. It's because of their salience and relevance and their interaction. That means there's a whole lot of information about some items being faster than others that I don't know why. Right? So all the other reasons and ways in which these natural scenes varied from each other are influencing response time, and I don't have any information about that. That's all I can do. How you can compute this then using saved code is, again, the varchor option. I think this is part of Elmer test if memory serves, but I could be wrong about that. That is this piece of output right here as a data frame in which the variance components are in the 4th column. So I'm going to save each of these from this model. So cond1 is the name of this model for me. This is going to be the subject intercept variance, the item intercept variance, and the residual. So it's the row of that table and then the 4th column. So this is where printing the table to make sure that you have them in the right order versus subjects versus items is important. So as predicted, if I go down here and compute R-squares for each kind, here's the one for subjects, what it was minus what it is over what it was. Subject intercept variance did not change very much, which is what should have happened because we didn't try to explain it. Item intercept variance did change, that's the 0.26 we computed earlier, and residual variance did not change because we haven't added anything. If I want to get a joint hypothesis test for how well my item predictors explained variability, then I can do this function right here. So this is what's known as a multivariate Wald test more generally in the literature. If you're using a chi-square, I would call it a modified version since we're using an F instead. The difference is whether or not you're using denominator degrees of freedom. We are doing that here with the Satterthwaite method in particular. So what this code does is simultaneously test whether that slope, that's the relevance main effect, the salience main effect is the 3rd spot, and the interaction term, whether those 3 slopes jointly are different than 0. So it's the analog to the F test for your model in regression, but this is just for the item model specifically in this case. And it looks like, yes, even though the interaction term itself wasn't significant as a set, they do significantly predict log response time. And so I would report that down here like this. Random variance left over. As you might imagine, yes, we still have some. So Renova I'm asking for again so that I can test of the item variance that's left, whether that's different than 0, and yes, indeed it is. So conceptually, when I go back to the equation, let's see here, way back, there we go. This U right here has a different interpretation after you have predictors in the model than it does before. This is now U discrepancy after controlling for relevance, salience, and their interaction term. Apparently I need some more coffee. So this is then like each item gets its expected response time based on relevance and salience, and then this is how far off from that the prediction is for that particular item. So these are like U's left over. For that reason, these are sometimes called level 2 residuals, and I'm not going to do that to you. I think that's confusing. I just call them level 2 random effect variances left over. So this U with an I subscript is conditional, it's left over. The one with an S currently is unconditional, but that's about to change. Okay, how are we doing? Okay, ready for another model? Let's get the subjects involved. So I'm keeping all 3 fixed effects related to my items for right now, even though the interaction was not significant. And I'm adding in effects for my H groups. So this subscript pattern then, why is this 001? Subscript queen, we got it, go for it.
Yeah. Yeah, the first subject level predictor. So
Yep.
the S.
Yep, it's where the S is. So this is the first subject predictor, this is the second. And this is years minus 65. This is the nested predictor that only applies within the older group. So it's zeroed out completely in the younger group, so it won't add to their score. So this is how many years past 65 they are in the older group specifically. So age is semi-continuous as a predictor in this model. We throw in the fixed effects in the usual way, and note that I have a comment here. Relevance and salience, I moved to the end of the line because in R's output, it's going to do that to me anyway. I've tried to figure out a workaround to this and I have been unsuccessful. But that is important for asking for follow-up tests involving these slopes. You have to know in the order in which they appear in the output. So we're going to throw those two in. Here's my fixed effects. Blow those up a little bit. So my relevance and salience effects and their interaction terms are pretty much the same numbers as before. Is that surprising or unsurprising? Question, Johanna.
Sorry, I just wanted to ask again, what's the difference between the star and the because I slightly remember that it's whether the main effects are included or not, but maybe that's also wrong.
Yes, no, you're exactly right. The colon is referring to just the interaction term. The star also includes all of the lower order main effects that would be part of that interaction term. So the star is less typing, but less transparent. So I deliberately hide that from my students, to be honest, because I want them to understand what they're asking for and have it match the code. But if you know that and you want to do less typing, then just the star would replace these two things. Yes, indeed. And I believe that is not just an Elmer thing, that's a general, like, R formula convention, from what I understand.
Thanks.
Sure. Any other questions at the moment? Okay, let's see what happened. My question to you then was the coefficients for relevance and salience and their interaction are pretty much the same as they were in the previous model. And my question was, is that surprising or unsurprising? It's normal because we have subject predictors. Yeah, the item predictors and the subject predictors should not be correlated, right? They're completely different dimensions of sampling. So we would not expect collinearity among the predictors or relationships among the predictors to wiggle these things around. The new ones that we have are these two right here. What happens if you are an older adult relative to a younger adult to your mean response time? Yeah, I'll take gestures. Up, down, up. Yeah, so up is bad in this case. That means you are slower the older you get. Trust me, it happens. So relative to a younger adult in the 18 to 21 year group who would have this predicted intercept, so this is for an item with relevance 3, salience 3, and now specifically for a younger adult, older adults are going to have slower mean response times on the log scale by 0.59. Then this one. What happens if you're even older within the older group? Up some more. Yeah, so for every year older you are than 65, in the older group specifically, mean response time is higher by 0.02. So both of these things appear to be relevant, pun intended, in predicting response times. There we go. Effect size. So here's another softball question. Are you familiar with that expression, by the way? I say that a lot. So a softball question is like, so in American baseball, like the pitchers are throwing the ball at you at like 90 miles an hour overhand. And if you play, we don't have like women's softball as a sport that people would pay money to watch, but we have it in the Olympics and we have it in college. And women's softball does this windmill thing where they like wind their arm up and then they throw it at you as hard as they can, and it's like 60 to 70 miles an hour. If you play what is known as slow pitch softball, which is what you could do like for recreational leagues and that kind of thing, they just take the ball and they go like this, like underhand, just nice and easy so that you can hit it. So the expression softball question is referring to like a question that should be easy to hit, that you're not trying to be tricky or have them do anything difficult. So I believe this to be a softball question. The subject predictors that we just added related to how old someone is, which of my 3 piles of variance should they have explained? Subject, item, or residual? One vote for subject. Another vote for subject. Yep, that's it. These are subject variance is all the reasons why some people are faster than others. Some of those reasons appear to be tied to chronological age. How much? Quite a bit, as it turns out. 87%. I know, right? Aging is bad for you. I would not recommend it. 87% of all the reasons why some people are faster than others has to do with their chronological age. Now that is impressive if I think about it as 87%. But would it be accurate to say that the subject predictors explained 87% of the variance in response time? Could I say that? No, that's not complete enough. That's misleading. Because how much of the variability in response time was originally due to subject differences in the first place, we need to know. I believe that was 27%. So what I have is 87% of the 27% that reflected subject mean differences. It's a lot less impressive when you put it that way, but that's accurate. Likewise, on the item side, I think I had 18% was due to item differences. My model explained, the item predictors explained 27% of the 18%. So that would be how you get back to how much actual response time in total the model explained. And I'll have a computation for that at the end of this, actually. So yeah, 87%. So 87% is due to the subject predictors. The same 25 or 26% was due to the previous item predictors, and we still haven't explained any of the residual. So here's the change relative to the previous models, which you can also report. If I want to do a joint hypothesis test for the two slopes to get assessment of the overall effective age, I can do that with this command. And note, I've had to add more zeros. So these commands grow as your model gets more complex, and you have to know exactly what order the output is in to know where to put the ones and zeros. So this one refers to the slope for the older dummy-coded predictor, and then this one refers to the slope for years over 65. The last place is for the interaction term, excuse me. So that is a giant F, as you might expect. So do you think there's any remaining reasons why people would differ from each other? Besides age? Probably. That's an empirical question. Renova is our friend to answer that. It looks like we still have a highly significant likelihood ratio test. So yeah, we'll keep the subject variance in. That 13% is not nothing. Okay, random slopes are the next part of the story. So right now we're assuming that subjects differ from each other in only one way, in their mean response time, and that's it. So that would mean that we would expect the same correlation of item trials nested within people, regardless of what kind of item it is. Got a question, Johanna? Is that better? I'm working on my accent.
Yes, great.
Okay.
I have a question. So if the variance would not be relevant, and if we would take it out of the model, for instance, the item level variance or the random effects there, how would the estimate of the subject level estimates be more precise? I mean, they should be uncorrelated, right? But I don't know, how would the model change if I would take out of them?
Great
the other
question.
one would.
Yes, so I've actually done some simulation research on this, and I can say that you should not take it out. What happens is only when it's exactly 0 is it safe to take out, because otherwise you end up with potentially the same fixed effects with respect to your subject predictor. So this is subject variance we'll focus on for this example. You end up with the same fixed effect estimates, but your standard errors are much too small because they still need whatever leftover variance you have to be part of that. And you end up with too high of type 1 error rates and things like that. So I'm doing this sort of as a way to demonstrate how you could answer that question. Like, after controlling for the design features, are my subjects or are my items truly exchangeable? Without that intercept being random, you're assuming that they are. So I would leave it in. I probably wouldn't do this in practice, but if I wanted to make that point, then I could say, yes, I still have significant variance to be explained, and it needs to stay.
Okay. Thanks.
Sure. And the other part of this to keep in mind is your power to detect these things. And that was actually the reason that motivated the simulation research, is what about random effects in small samples? In this case, we have 151 subjects, which is not bad. But if I had a very small subject sample size, I would want to be extra careful to not remove something that could be a type 2 error. Like, I could need it and I missed it because I didn't have enough power to detect it. Okay. So, adding to the model then, examining the potential for subject differences of a different kind. So, modifying and elaborating the way that we're thinking about individual differences, past just mean RT, to say, are there individual differences in how effective these item differences are? So do you think some people's response times do have a greater benefit of relevance or salience than others? Potentially so. So we can look at that. And because salience had a larger effect, like per unit salience, I picked that one first. So here is the new term that I'm adding that is going to form a random slope for salience. And I have a typo in that, 1 extra 0, there we go. So this is UO2S, and it's 2 because it's tied to salience being 2. So they match. And I get an S on it because this is a subject-specific random slope that is going to have a variance across subjects of this right here. So note the U's for the subjects now are in a matrix. I call this the G matrix. Sometimes it's abbreviated as T in literature. The idea is that because both of these random effects come from the same subject, they should be allowed a correlation. So in adding this random slope, what we're actually adding as model parameters is its variance across subjects and its covariance with the subject random intercepts that were already there. In R, the covariance is rendered as a correlation instead, but you can get either way, it's the same idea. So we're adding that inside the subject random section. That's very important. Likely, if you put it over here instead, it would break your model. So I would not recommend that. So I'm asking whether the salience slope varies across subjects. Does salience have the same benefit to improving response times for making them faster if it's high salience versus low salience? Survey says, well, here's what we get. Now, does that look like a lot? Do you see anything in front of you that would help me decide whether or not I need that new variance? Nope. What do I need to do? Likelihood ratio test, yes. Whenever the question is about something related to variance in your model, the answer is likelihood ratio test. Like always, just that's a guiding principle. Likewise, in generalized models, if you're asking any questions about overdispersion, so do I need more variance than the model predicts, that's likelihood ratio test. So it's a technique that shows up across many different disciplines in statistics. So no, I don't know if this is a lot. Numerically, it doesn't look like very much. Correlation, it looks like it's fairly small as well. So we can use our friend Renova to find that out. The one that I'm interested in, even though it does all three combinations of removing random effects, is this one, salience 3. And the likelihood ratio test is 8 for the test statistic. So it looks like it's significant. This is a case where I might want to report the mixture p-value instead. So I went ahead and did that down below. So on average, the salient slope is minus 0.14, which is close to, but not exactly the same. It's the same to 3 decimal places in this case, but if you keep going, it's a little bit different because it's the mean of the subject salient slopes now. So it has a different interpretation. In terms of doing the mixture, if I wanted to report that version instead, what I did is compute the difference in log likelihood. So that's my test statistic right here. Looks like it didn't render enough decimal places over here, so boo R. Then I have the p-value for degrees of freedom 1, which would be for the situations in which the variance would have gone negative if we let it. The p-value for degrees of freedom 2, when it would have gone positive, and then the weighted combination of these two, 0.5 times each, gives me my mixture p-value. So this would be the more correct version to report. However, if your hypothesis test from RENOVA using the regular chi-square degrees of freedom is already significant, you don't need to do this. This is just going to be more significant. But for purposes of demonstrating the rightest way to do something, I threw it in. So we know that our slope variance is different than 0. If I wanted to try and explain what it means to somebody, that's where a random effect confidence interval can come in. So before we did these for the intercepts, we can do these for slopes. So for the salient slope, the middle is the fixed effect, and the random variance under the square root sign is for the random subject salience slope variance. So I'm asking about the variability expected from the variance component in my sample. So if I do the math, work through that, here is the range. So this is the range of the slopes that we would be expected in 95%. They're all negative, so everybody gets a benefit from salience, but the size of that benefit differs by people. Some people get a benefit of 0.2 per unit salience, and some people only get a benefit of 0.04. And here's how I computed this in R. So step 1, figure out where my numbers are. So fix F right here is where the fixed effect coefficients are. I printed it as a data frame, so it's only one column, but then we have all these rows. So the first thing I had to do is figure out where the fixed slope is, and it's right here. So I'm going to save that as an object. So row 3, column 1. Then I needed to figure out where the random slope variance is saved to. So that's varchar. And it is going to be this one right here. So that's the random variance, and that's the standard deviation. Any guesses as to what the third row would be? Because it has salience in it too, which could be confusing. What is that referring to? What do you think? I'll give you a hint. The fact that there's 2 variables listed here is noteworthy. All the other rows only have 1 variable. The interaction, right idea, not quite. This is variances and the picture of matrix covariance, ding, ding, ding. Yeah, so this is, not that you can tell this from the label, mind you, right? This is why I'm telling you this. This is job security. This is the covariance between the subject random intercepts and the subject random slopes. And then this is the correlation. So 0.06 is the negative correlation we saw in the output earlier. But I don't need this row to compute anything. Instead, all I need to do is save each of the variances. So I have subject intercept variance, subject slope variance for salience. item intercept variance and residual. And so then I can compute my confidence intervals using that saved information, and I can also compute, for the next model, effect sizes. So we're keeping the salient slope. What about relevance? Could it have a random slope over subjects? Could subjects have differential benefits to how relevant the change is in their response times? Sure. So this could be a third source of individual differences. So in this model, here are the 3 random effects pertaining to subjects. UOOS is still the random intercept, but it takes on a different interpretation. In the same way that the fixed intercept is conditional on the predictors being 0 that have fixed slopes, the random intercept is conditional on the 0 values of the predictors that have random slopes. So UOOS is the random intercept deviation specifically when relevance is 3 and salience is 3 in this case. It's further conditioned on that. What is actually happening under the hood is that by allowing different slopes for different people, you are allowing heterogeneity of variance across subjects as a function of relevance and as a function of salience. And so that means the U-intercepts would be different at different points along those variables as people spread themselves out. So now my G/T matrix has a 3x3. So how many new things did I actually add to my model in adding this one new random slope variance? And don't say 1. How many new parameters are actually in my model after adding a random slope variance for, actually, relevance is the one that I added, excuse me. That's the new one. What do we think? Not just 1, but more than 1. Because I got to fill out that matrix. 2 is what we had before. So we started with this one, and then we added, this is 2 here, so we added 2 things. If I add another row, I've added 3 things. So because we have 2 random subject slopes, I'm also allowing covariances of the random effects for subjects that were already there, the intercept and then the first slope. So I'm adding 3 altogether. So now I have salience and relevance inside the subject random effect statement in here. Scrolling down, here's the new line. So note, this is the variance, and these are the correlations. And I'm not entirely sure which is which, to be honest, because they're not well labeled. But I'm guessing that it is 0.14 is with the intercept and 0.08 is with the other slopes. But we'll have to look at the output to be sure. And I can't tell by looking whether or not I need to keep that. So we'll do likelihood ratio test with our friend Renova. Here is the new line. Doesn't look like it. I can do a mixture version of that test down below to try to get a more specific correct p-value. Still doesn't matter, so no. Here's random effect confidence intervals just to make the point. So this is all the variability that's expected across subjects in the effect of relevance, 0.09 to 0.0, and that is not a significant amount, so we won't need to keep it. And here's where the math to do all of these things using saved objects. So now, based on this table, I can tell which correlation is which. So this is intercept and salient slope. This one is relevance and intercept, and then the 2 slopes are correlated 0.8 in this case. So it looks like people who get a bigger boost for salience get a slightly bigger boost for relevance. Small effect, but it's positive. And for relevance, the people who get the biggest boost in relevance tend to have the slowest response times. That's what being high on both would mean. All right. 2 more models. Do we have it in us? Do we have the strength for 2 more models? We can persevere. So to avoid dragging this out much further, I decided just to go ahead and explore all possible interactions. I'm going to let the extent to which salience, relevance, and their interaction predict response time vary by age and age slope. So this is where the notation gets fun. Let's see how many of these I screwed up, because you can only notice it when it's in front of your presentation. So this one right here, does that one look okay? 011. So by the same logic as before, this is the interaction of relevance being older. So the first subscript is still 0 because we don't have any trial variables. The second subscript is 1 because that's what relevance was before. The third subscript is 1 because that's what older is before. So 011 in this is like a combination of the two. That's your interaction term between relevance and older because each is the first predictor of its kind. Likewise, 021, that one is for salience and older. The three-way interaction term is 031. And then we get the same pattern for years 65. It's the second subject predictor, so these are 012, 022, and 032. And I took out the random relevant slope that we did not need at this point. Look, I got him right. Yay me. You got to celebrate your victories. So let's see how ugly this model looks, throwing all the interaction terms in turn. Okay, so lots of stuff to look at here. If I look at the highest order interaction, which is relevance by salience by years over 65, that one looks to be non-significant. Same thing with salience and years 65, and same thing with, where did it go? Relevance, that one's marginal. So it looks like we can probably simplify the model before we try to interpret it. Here's how I can test for the new interactions with older simultaneously, all three of them. The 1 is in the spot where the interactions with older are according to this output. I can do the same thing for an omnibus test of the interactions with years 65, and this one is not significant. This one is not significant currently. But I can take out the highest order interactions. I did that one by one, and it looks like the story didn't change, so we can get rid of all three. So then we get to our final model, which has the 3 interactions with the older group in it still. So this is what we're adding relative to what we've had before. All right. Question, Johanna.
Sorry, just to make sure, you took out the random slopes, right?
I took out the random relevant slope because it was not significant. The salient slope is still in here because it was. And then with respect to the fixed effects, I took out the 3 interaction terms with years 65, with relevance, salience, and with relevance by salience, because none of those was significant. And if you take them out one by one, the story stays the same.
Okay, because I was just confused because I thought that you said to my question that you should keep them in anyways, but maybe I misunderstood that.
In that case, ideally, you would, if the random slope is really not there, you would not want to keep it.
Okay.
Because it will cause estimation problems.
Okay.
The consequence of that is potentially, if you don't have enough power to detect it, a type 2 error in which you should have kept it. With 151 people, I feel pretty good about that. In terms of the variance explained, though, the fact that it's not there is going to change what the role is of the fixed effect interactions.
Okay.
So yes, there are some folks whose philosophy is keep everything random, but practically speaking, that's not going to work in most cases. I also did try, by the way, a random relevance by salience interaction, and that broke the model. It wouldn't work at all. So I'm keeping 1 subject random slope and 1 intercept, but I have 5 variance components altogether, which is what makes the estimation tricky.
Okay, thanks.
Sure. So we can go through the list here. In light of our new interaction terms. So this two-way interaction is now conditional on this three-way interaction, and the three-way is significant. So what people would call the two-way is actually a simple two-way interaction, which sounds like a misnomer to me. But in practice, what kind of person is this relevance by salience interaction for, given the three-way interaction? It's conditional. I think folks are typing. I'm watching. I wish Zoom had the little dots to tell you when someone's typing. That would be really helpful. Who is the relevance by salience interaction for, given the three-way interaction term? That is the question. Go for it.
Is it for the younger ones, because they are the reference?
Yep, exactly right. So we have the same pattern as before. So let's start with the effect of salience as the baseline. So in the younger group, the more salient the changes, the faster it's detected. That is conditional. The first line right here is conditional on relevance of 3. Then as relevance increases in more relevant changes, the effect of salience is more negative, so it's stronger in the younger adults. What happens in the older adults? The rule is the same. The only difference is the order of complexity. So the two-way interaction term here is for younger adults. The three-way interaction term says how it differs in older adults. What happens to it? Does the relevance by salience interaction become more positive, less positive, more negative, or less negative? Oh, yeah, take gestures. Yeah, more negative, stronger. So that's how I would approach this problem, is to think about the extra benefit of relevance or salience when the other variable is high is not significant in younger adults, but it is significant in older adults. You could also go at it through these ones instead. So this one says what the effect of relevance, how it would differ in the older group, specifically for salience of 3. So we do that one. If I look at just those two, which pattern is it? Conditional on a salience level of 3 for both. Relevance in the younger adults has a significantly negative slope. But what happens to that slope in the older adults? Oops, lost it. That one and that one. Slope of relevance in the younger group is negative. The interaction term of relevance by older is positive. What's happening to it? More positive, less positive, more negative, or less negative? This one is less negative. Yeah, flatter, weaker. So at a salience level of 3, the older adults don't get as much boost from additional relevance as the younger adults do. Their effect is mitigated or diminished. The same thing is true with the main effect of salience, conditional on relevance of 3. That negative slope is less negative in the older group, but non-significantly so. And then you can put this on it if you wanted to talk about how that pattern changes as a function of relevance. So three-way interactions have 3 possible interpretations. They take each of the 2 ways underneath them and make them more or less positive or negative The two ways then take the main effects and make them more or less positive or negative. And this is the point at which, if you're writing this results section, your readers are like, oh my God, can you please just make a picture already? I can't keep this in my head. So we did that. So here's how you can figure out what the simple slopes would be according to the model. So I wrote this one out. This is the entire model right here in the first block. The predicted relevant slope is found by taking all of the fixed effects that have relevant in it and then factoring that out. So the ingredients are given in this line right here. So this is how you can ask for the relevant slope for any level of salience and for any age group. Likewise, if I figure out what the salient slope terms would be, I pull all those down, factor out salience. Here's how I would get to what the salient slope would be for any level of relevance or older. And then the two-way interaction. That itself then can be computed in younger people as the main effect of the two-way interaction, or adding on the three-way interaction to get it to what it is for older folks. So I did some contest 1D statements for that, in which, again, these numbers are multipliers for what goes in the parentheses. So there's an implicit 1 here for each of the simple slopes, for instance, that down below is referring to. So I can get the relevant slope for younger, for older, significance test for each of those, salient slope for older and younger, and then two-way interactions for older and younger. And then I made a picture. So in this model, I want to show a three-way interaction term. That means that I need to systematically vary younger versus older. I need at least some amount of high versus low relevance and high versus low salience. And I also might want to show what happens in the older group as a function of the slope of year 65. So the way that I chose to do that, let me open the Excel sheet here just a second, is to make fake people in the based on the patterns in the original data set. So let me open up Excel so I can show you what this looks like. Otherwise, the code below will not make any sense. So this is a separate tab that I made. These are fake people. So this is a person whose score on years 65 is 15, which makes them 80. They are older. And here's a range of relevance values for them to plot. And then salience 3 at -2 puts it at a 1. Then I have the same kind of item for somebody who is older at 65. And then I have it for a younger person. And then I have the same pattern for a slope or a value of salience that's high. So note in this data, I filled in -99 so that they'd stay in the model, but what's not here is any kind of response time. So what I'm going to do is feed this object into R and use the predict function based on the last model to fill out a column of predicted values, and then I can make a plot out of those predicted values. So I like this method of making up fake cases, because then you don't have to anticipate exactly what the model's going to have. You can get a range of predictions and then choose what to plot, and everything gets updated if you do change what's in the model. So I'm reading in that sheet labeled fake because these are fake cases that I'm adding. I'm then augmenting the data frame using the predict function to generate a new outcome called y hat with no random effects. So these are just based on the fixed effects. And then the tedious process of creating different lines for the different combinations. And here's my picture. There. It's not too pretty, but it works. So what this picture is showing then is relevance on the x-axis on a scale of 1 to 5. I have predicted log transform response time on the y-axis, and then I have different colored lines for different aged people. And I anticipated that the oldest people would have the highest response times, and so that's why that legend is oriented in the same way as the lines. So the purple lines are for somebody who is age 80 to an item that has either low salience, the top one, or the dashed line is for higher salience. The blue lines are for somebody who's 65, and the red lines are for somebody in the younger group. So note the purple and blue lines have the same slope because there's no difference in the effects of relevance or salience as a function of years over 65. The only difference is between older and younger. So the blue and purple lines have a different slope than the red lines because we have that three-way interaction allowing the effect of relevance and salience interaction to differ by age group. So that would be the story there. Okay, how are we doing? Now here is a non-softball question for you, okay? This is like at least fast pitch softball, maybe even actual baseball where they're throwing things at you at 90 miles an hour. Which again, miles, not helpful. Hours, not helpful. Here's the list of coefficients. We've already decided what relevance and salience do. Like, hang on, oh, this one, that one, and these two. Those are item predictors, right? Which variance did they explain initially? Relevance, salience, and their interaction? Item intercept variance, yep. Likewise, I have the two subject variables. Which variance did they explain? Subject intercept variance. Now here comes the tricky part. I'm going to start with this one. Salience by older. Which source of variability should it explain? Because it's both a subject thing and an item thing at the same time. Your choices are right here. There's 4 choices: subject intercept, subject salient slope, item intercept, or level 1 residual. Those are the 4 choices in terms of what the new interactions can explain. Which of those 4 is explained by salience by older as a fixed interaction? We got 1 vote for the second with a question mark. Second without a question mark. Second with less words and no question mark. Yeah, it's the salience slope. So conceptually, this line right here for salience, this is all the reasons why subjects differentially benefit from changes of higher salience. One of the reasons for that differential benefit could be the fact that they're older. Now, this interaction term per se is not significant, but the idea still holds. So interactions with the predictor that has the random slope explain that random slope variance. So you're all exactly right. Not as tricky as I thought. What about relevance by older? Which of the 4 does it explain? Let's go through the list. Is it just a subject thing? No, can't be subject intercept. Does it have anything to do with salience? Nope, can't be the slope. Is it just an item thing? Nope. What's left? What's left? Residual question mark? I pronounce the question marks, I like to. Residual? Ding, ding, ding. That's it. Now, had I retained the random slope for relevance, it would have predicted that instead. Question. Go ahead.
This is a very basic question, but if we have these predictors included, the variance gets smaller, right?
Theoretically, yes.
What happens then? Also, the residual gets smaller, right?
It depends on which predictor. So in this case, relevance by older has to explain residual variance because there's no random relevance slope across subjects for it to explain in the same way that salience by older explain the random salience subject slope.
Okay.
Yeah, not a stupid question. These are not basic, is what you said. Not either of those things. This stuff is tricky. How about the three-way interaction? What's it going to explain? By the same logic. Say it again. Residual, yeah. And what kind of random slope would have needed to have been in the model in order for it to explain that instead? Relevance by salience as a random interaction slope. Then it would have explained that. And yeah, I tried to estimate that, it wouldn't estimate. So now so this is basically where the chapter example ended. I then tested heterogeneity of variance, and I was unable to figure that out, how to do that in R, unfortunately. But there's one more thing that I can do to talk about effect size. Now, whose head hurts based on trying to keep track of all of this? Anyone? Yeah, me too. Yep. It gets increasingly tricky to figure out which variance component should be affected and then see it actually happen, because these things wiggle around across methods of estimation. So you can see things go up a little bit or down a little bit just because of these fluctuations. For that reason, and also to try to get a more comprehensive measure of effect size, one other thing that you can do that's complementary is to compute what I call a total R-square. And that is based on the exact same process and logic as in a single level regression model. In single level regression, there's only one possible R-square because there's only one possible pile of variance, right? There's just the E variance at the end of the line, the end. So we're used to interpreting R-square in single level regression as the proportion of variance explained by the model. Another way to interpret it is if you take your model, fixed effects, and use those to create a column of predicted outcomes, like a y-hat for your whole sample, and you take that column of predicted outcomes and you correlate it with the column of real outcomes, that's R, and if you want to get to an R-square, you square that R. And so that is another way of thinking about R-square, is the square of the correlation between the predicted outcomes and the real ones. So that's what I'm doing here, is building y-hat in my data set. So this is not in the fake people anymore, this is the real people, using the predict function from my last model, and then shutting off any random effects from being contributed to the prediction, so just the fixed effects. I then estimate a correlation and square that correlation. This is where it's saved. And the answer is 0.28. So I can interpret that as in the same way that I would for single level regression. Of overall log response time, my model, fixed effects of all the different kinds, explain 28% of it. The end. That's a lot easier to talk about. So the pseudo R-squares are good for sort of zeroing in on specific kinds of variance for specific reasons. Like this is all the reasons subject means differ. This is all the reasons subject slopes differ. This is all the reasons item means differ. This puts it all back together again in one giant pile. 28% of the variance in response time was explained by my fixed effects. And note, turning on the random effects in this instance to me would be cheating. Random effects haven't explained anything. They are all the unknown reasons why subjects still differ in their means, in their intercepts, in their slopes, item differences, and so forth. So to me, those don't belong in an R-square because they represent error variance, reasons that are unknown still. But other people might logically disagree on that. All right, looks like I actually did fill most of the time here. So I promised Anna and maybe a few others that I had an example in M+, and I can go through that with the very few minutes we have left after I answer this question. Go for
Yeah,
it.
I just wanted to quickly ask, you said you could also have trial-based predictors, right?
Yes.
Would you then kind of, if you want to avoid the conflation, would you have two at each level, like the component or the between component, or how would that work for the, because you have multiple, right, the crossover of the
Yes.
levels.
So if it were something that had between subject variance to it is the key. So like if it were just the order of the trial, then that would not differ across people because everybody eventually sees the trials. But let's say it's something like, let's say that each subject had to respond about how much they liked that picture, something like that. So they have like a trial level specific predictor. You are absolutely right that it's not just trial level. Because if some people might like the pictures more than other people, that would become a between subject predictor. That would explain subject intercept and or slope variances. Some pictures might be liked more than other pictures, and that would explain item variance as well. So yes, anything that's a level 1 predictor that has variability across either of the level 2 units would then need to become a predictor at level 2 to allow differential effects at the between level as with the within level.
Okay, right. Thank you.
Yep, same exact principles. All right. Do you want to talk about M+ real quick? I have it open. So I fit the last model in M+ without a random salient slope because it wouldn't allow it. So I made a data set for M+ in the last part of this. I think it's in here. It's in the code online. I didn't print it in here. So this is using cross-classified models within M+. It's the same data set in long form. The only difference is that I only saved the variables that I needed. So up to here, these variables are in the data set. The others are I all needed to make. For cross-classified models, you need to tell it what both sets of ID variables are. So I have, for a cluster option and setting up the variable command, the subject ID and the item ID. Then in terms of predictors that are only to be used at the between level, you have to tell it which kind each is. So the subject predictors are the 2 age variables. The item predictors are the 2 item predictors, and then I had to manually build all of the interaction terms. So here under define, I built the relevance by salience 2-way interaction, each of the 2-way interaction terms with older, and then the 3-way interaction term of older by relevance by salience, and then those all get added to the end of my use variables. So in this program, you can't define interaction terms on the fly unless one of them is with a random effect. If they're observed variable interactions, you have to make them in the data. The type of the model is cross-classified. It's only available using Bayesian estimation. I put a little bit of information here about what the defaults are and trying to make sure that it truly converged by tightening the criteria. I'm using the median as the estimate of the posterior that's coming back as what our point estimate would be. Tech 8 provides additional information about convergence. That's useful. And so then the model itself has 3 parts. You have to specifically designate each type of predictor and where it goes. So log RT on the interaction of relevance and older, salience and older, and then the 3-way interaction, that goes into the within model. So anything that is both a subject thing and an item thing at the same time goes into the within model in this because we don't have any random slopes. M+ would not let me estimate a random item predictor slope across subjects or vice versa. So this is more limited than what we just did in Elmer. So I have those 3 interaction terms here. The between model for subjects then is where I'm providing the fixed intercept for log response time. So in brackets, there's only one fixed intercept regardless of how many cross dimensions you have. The random intercept variance for subjects then shows up here. And then the effect of my 2 subject predictors on my response time is the last line. For the item line, I don't need a fixed intercept because I already asked for one. I have a random intercept variance, and then I have the item predictors, relevance, salience, and their interaction. And then last but not least, the labels in the parentheses. This is the analog to how I can get simple slopes or predicted outcomes, like I did in Contest 1D out of Elmer. So I'm labeling each of these slopes. So the F in front stands for the fixed effect of old by relevance, for instance, the fixed effect of old by salience, and the fixed effect of old by relevance by salience. I labeled all of the others. And then down here in model constraint, these are new linear combinations of the model slopes. 3 of them are directly given, but I did it for pedagogical purposes to show you the pattern. And so then this is what the model implied slopes would be for the older group, which are linear combinations of the main effect plus the interaction that turns it on for older. So then this is a way that you can get further information out of the same analysis. In the output then, as I continue to scroll down, lots and lots of scrolling, of course, it then presents the results for the within level specifically, so those are my 3 interaction terms. Residual variance is my level 1 residual variance specifically. Here are the 3 item predictors, the 2 main effects and their interaction at the item level. Residual variance at the item level, that's going to be my item intercept variance left over. And then the subject level, here's the 2 predictors for age for that. Here's my fixed intercept. Here's my subject intercept variance left over. And then here's all my new simple slopes and interaction term parameters that I made. And that's that. So this approach would work better if you want to use latent variables or put a measurement model on these, but it's more limited in what types of random effects you can have is what I've learned. But if you want to do path models or latent variables, then this is the way that I would go about doing that. So does that help you? You asked about path models. This is sort of like the general setup, and they have examples in the user's manual as well. Okay. Ta-da! That's example 2. And it's 10:26, which means we don't have time to have much discussion. How about I follow up over email with what the plans are for the next unit that starts in late June? That work for folks? One of the things that Thorsten thought would be useful is to show these same types of cross-classified models for binary outcomes and the connections of how that ties into explanatory IRT. So I was planning on spending at least 1 session on that. How we spend the other 3 sessions, I think it can be up to you. So we can continue having that discussion like a month from now or so. How's that sound? Cool. All right. Any other questions before we call it a day, a week, a month? No, we're good. All right. I'll hang out for a few minutes after in case anyone does want to talk. But otherwise, thanks for being here. Johanna, go for it. Someone does want to talk. No, please.
What does it mean if there is a very high correlation between the random slopes over the random slopes?
If the correlation approaches 1, that's an indication that you don't need both of them. And so I would probably remove one or the other, or try to find some way to reparameterize it so that it can be both at the same time. So for instance, like if I had a 3-group variable and the difference between like the reference group and the alternative group was 1 slope and the reference versus the other was another, and those were perfectly correlated, then I might make a new variable to give a random effect to that's just like reference versus either alternative. And then that would get at the same idea but use fewer parameters. But generally speaking, if a variance goes to 0 or the correlation among the random effects approaches the boundary, then that's a sign that you don't need that additional source of variance.
Okay. And would that cause any problems in terms of the estimation?
Yes.
If I would.
Yeah, so if your model breaks in this class of model in which you have conditionally normal residuals, it is never the fixed effects that broke it, it is the random effects.
Okay, thanks. That's my last question. You can end.
Okay, well, it's 10:28, so we're not even late. But I want to thank everyone for your attention, for being here. Let me know if you need anything. I'm not holding regular office hours this summer, but I'm supposed to pick that up again in the fall. But you can reach me over email and I can talk to you as needed during the summer as well. So, sound good? All right, cool. Thanks, folks. Have good days. And let's see. No hand? Okay. All right. I'll hang out for a few minutes just in case. Bye for now.